So today in this lecture I will talk about scattering matrix and the transition probability. Here I will briefly discuss the meaning of scattering matrix and its properties. So as we have defined unitary matrix in the earlier lecture, that is so as we have defined that u t naught, it is equal to 1 minus iota integral t naught to t. It is a unitary matrix. It is dt1, it is hi t1 plus minus iota square and integral t naught to t1 t naught to t, and it is dt1, it is hi t1, and then integral t naught to t1, it is dt2 and hi t2. This we have defined in the earlier lecture. So and this can also be written as, let us call it as equation number 1, and this can be written as that u t naught is equal to 1 minus iota t naught to t. It is dt1 hi t1 plus minus iota square integral from t naught to t. It is dt1, then again integral t naught to t1. It is dt2 hi t1 and then hi t2 and so on, and let us call it as equation number 2. So let us now understand the meaning of u. Meaning of u. So for this, suppose system is known to be in system is supposed to be in state I at time t naught, and the probability of finding the system in state f. This is the state I and this is the state f at some time t is given by, at some time t is given by that b, it's a final state, it is u t naught whole mod square is equal to u fi, it is t naught, it's mod square. Let us call it as equation number 3. The average transition probability, the average transition probability per unit time for I to f is given by wfi it is WFI. This is standard definition. It is 1 over T minus T naught. It is UFI T comma T naught minus delta Fi. It's mod square. Let us call it as equation number 4. So in equation 4, if T minus T naught time interval is infinitesimally small, then it approaches to a definite limit limit at T naught approaches to minus infinity and T approaches to plus infinity. So this motivates us to define S matrix. Motivate us to define S matrix. So that S is equal to U infinity to minus infinity. So this is known as S matrix. So after this, let us now discuss how scattering matrix related to transition probability so assume that before time t1 and after time t2 h is equal to h naught and perturbation acts only during the interval t1, t and t2. So only for this interval perturbation will act, and in rest of the region no perturbation will be there. Means before time t1 Hamiltonian will remain h naught, and after this time t2 Hamiltonian will remain the same. So then in state and out states are defined as in state and out states defined as that A in is equal to A t1 approaches to minus infinity. Let us call it as equation number 6, and similarly A out can be defined as A t2 plus infinity. It is equation number 7. So now operator S provide link between description of the system before t1, where t1 approaches to minus infinity, and after t2, that t2 approaches to plus infinity. Thus A in is equal to SA out, such that SBA, matrix elements of S, they can be calculated as like this: out B A in. So this is equation number 8 and this is equation number 9. So here A and B indicate quantum numbers necessary to specify initial and final states. In compact notation, it can be written as that SFI is equal to FI, it is out and it is in, and let us call it as equation number 10. So this part tells us about the importance of S matrix. Or in other words, we can say that it is the important property of S matrix. So now another important property of S matrix, that using S matrix we can calculate the transition probability, right? So now to do that, let us proceed as follows. So in equation 2, using equation 2, we can write down that S is equal to U infinity to minus infinity, and it can be written as 1 minus iota integral minus infinity to plus infinity. It is dt1 hit1 plus minus iota square. It is integral from minus infinity to plus infinity. It is dt1 and minus infinity to t1. It is dt2 and hit1 and hit2 plus and so on. Let us call it as equation number 11. Now consider its second term. That is, let us consider this term. So if we consider this, let us call it as S2, and it is equal to minus iota square integral minus infinity to plus infinity. It is dt1 integral minus infinity to t1. It is dt2 and hit1 and hit2. And if I interchange this, then negative will become positive. Interchange this limit, so it will become minus I square minus infinity to plus infinity dt1, and it is t1 to infinity. It is dt2 hi t1 and hi t2. Let us call it as equation number 12. Now by interchanging variable of integration, variable of integration, that is from t1 to t2, we can write that s2 is equal to it is minus iota square, its integral from minus infinity to plus infinity, it is dt2 integral from minus infinity to t2, it is dt1, it is hi t2 and hi t1. Let us call it as equation number 30. Now 13 plus 12 gives us 12. This is twice of s2 is equal to minus iota square, it is common, so it can be taken outside, so inside will be, it is minus infinity to plus infinity, it is dt2 integral of dt1, it is hi t2 hi t1 plus minus infinity to plus infinity, so here it is also minus infinity to t2, and it is minus infinity to plus infinity dt1 and t1 to infinity dt2, and it is hi t1 and hi t2, right? So this equation can be written as that s2, from here I can write down s2 is equal to minus iota square over 2 can be written in the form of 2 factorial, its integral from minus infinity to plus infinity, it is dt1 and then dt2 hi t1 and hi t2, and its integral from minus infinity to plus. I basically clubbed these two in a way, and here this is multiplied by t, right? So let me write down it clearly. Yeah, so it is dt2, it is t hi t1 and hi t2, so it can be written like this, and let us call it as equation number 14. Here t h I t1 and hi t2, it is equal to hi t1 and hi t2 for t2 is less than t1 and hi t2 and hi t1, it is for t2 is greater than t1, and let us call it as equation number 14, and this is known as time ordered product. Right? So this we have to keep in mind. So now in terms of Hamiltonian density, now expressing all these things in terms of Hamiltonian density, so for that let us proceed as follows. So here let us call it as HIT is equal to integral of d cube x Hix. So therefore S matrix or second term can be written as minus I square by 2 factorial. It is because this is sitting here. If I go to here, because let me, yeah, so if I try to look at this part here, integral is with respect to time, and here it is the integral with respect to spatial. So these two collectively can be written in the form of a 4 vector, so 4 volume space. So things can be written in this form of a 4 volume space, means volume in 4 dimension. Here 3 are the space coordinates and 1 corresponds to the time coordinates. So keeping this in mind, if I put it here, so therefore I can write down second term S2 as d 4 x1, its integral d4 x2 and here it is Hix1 and Hix2, right? So this is in terms of Hamiltonian density we have expressed our result. So similarly, let us call it as equation 14.1. So generalizing this equation, we can write down expression for Sn is equal to minus iota raised to power n over n factorial. It is d4x1 integral and integral d4x2 and so on d4xn. It is t Hix1, Hix2 and so on Hixn, right? So we can write down it in this way. Let us call it as equation number 16. But let us talk about only up to the first order perturbation. So up to first order perturbation we can express, so up to first order perturbation we can write that SFI, it can be written as delta Fi minus I integral d4x f Hix into I, right? And let us call it as equation number 70. So this is the equation number 17. So our purpose to evaluate this term. So to evaluate this, let us recall an identity, or as we know that hix is equal to e raised to power ip dot x, hi naught is equal to e raised to power ip dot x with negative sign. So therefore, using this we can write down that f hix, it's I. Now its integral in 4 dimension must be equal to its integral in the 4 dimension e raised to power iota pf minus px, pf minus pi dot x into f hi into I, right? And this is basically, if I solve this, then this is a standard value. It is 2 pi raised to power 4 del 4 pf minus pi. It's a delta function. It's the value of this integral. It will be equal to this one, and this will remain as it is. And here, because for this I have used this equation number 17. And another thing is that here hi basically it can be considered equal to this one, right? So this is equation number 18. So therefore SFI means equation number 17 can be written as SFI, it is delta Fi plus minus iota integral d4x, it is f, it is hix, it's I, and if I put its value here, then this is equal to, using equation 18, this can be written as delta Fi plus minus iota 2 pi raised to power 4 delta 4 pf minus pi, and it is f, it is hi, and it is hi, and it is I. So it is equal to delta Fi plus iota 2 pi raised to power 4 delta 4 pf minus pi into minus f hi and I. This we have put together in this way, and let us call it as equation number 19. Sorry, equation number, yeah, we call it as equation number 18.1. Or in short form, it is delta Fi plus I 2 pi raised to power 4 delta 4 pf minus pi, and it is Tfi. This is equation number 18.4. So here Tfi is equal to f hi, and it is I with negative sign, so it is equation number 19. So therefore transition probability, now the transition probability now the transition probability for large T from a state I to state F where I is not equal to f is given by, it is p limit t approaches to infinity, and cft its mod square, it can be written as f si its whole mod square, and it's basically the square, so it can be written as 2 pi raised to power 8 using equation 18. Using equation 18 here, and we can write down it as 2 pi and delta 4 pf minus pi, and it is delta 4 0 and tfi its whole mod square. But delta 4p is equal to 1 over 2 pi raised to power 4 e raised to power minus iota p mu x mu in the 4 vector form. It is d4x, its integral, and del 4 0, it is equal to 1 over 2 pi raised to power 4 into volume into time. It's a volume into time, so from here I can write down that volume into time can be written as 2 pi raised to power 4 into del 4 0. So therefore wfi, therefore wfi transition rate per unit macroscopic volume, it is p over vt. So let us put their values. So summation will be there, so it is the summation 2 pi raised to power 8 del 4 pf minus pi into del 4 0, and it is tfi its mod square whole upon bt, and bt will be this one. If I put its value here, so it will become 2 pi raised to power 8 and del 4 pf minus pi, and summation can be taken here, and del 4 naught and tfi raised to power this, and bt will be 2 pi raised to power 4 into del 4 naught. So this will cancel out with it and this with this. So now wfi, it can be written as 2 pi raised to power 4 and summation over del 4 pf minus pi delta 4, and it is tfi its mod square. So this is the required expression for transition rate. So this is the required expression for the transition rate, and for the evaluation of this we have used the idea of the scattering matrix, right? So that's all for this lecture.